Hope to God this is working. I don't want to have to record. I'm screen sharing, I'm recording, and I'm presenting on the thing.
You're not.
And I'm not muted, I don't think. Because it's got the mic.
Oh.
Okay, everybody, we're gonna get started. Man, yeah, this mic sucks. If you guys can't hear me at any point, just yell at me to speak up. Okay. Okay, so we're gonna get started with our nomenclature. So for this exam, you'll just have to know alkenes and all the previous stuff that we've learned before. So now that we've learned alkenes, that's gonna be our highest priority functional group. And so the rule for when we have a bunch of double bonds, like in question 1, is we're gonna want to try and get as many of those double bonds in the main chain as possible. So if you'll notice, we can either get a chain going this way and we get 3, or we can go this way and we can get 3. We can't get 4, so 3 is going to be the maximum. And so from there, we just have to figure out which one's going to give us the longest chain with all 3 of those double bonds. So if we go straight across, we're just going to get 1, 2, 3, 4, 5, 6, 7. If we go kind of up, 5, 6, 7, 8. So the red gives us 8 carbons and 3 double bonds, whereas the other one only gives us 7 carbons. So we're going to go with the red. And then again, our alkenes are going to be our highest priority group. So we want those to have the lowest number possible. So we're going to start numbering from the bottom right like I did here, because that puts our alkene on carbon 1. If we numbered it the other way, starting from the top right, we wouldn't get to an alkene until carbon 3, and that's not good. So we're going to identify our parent part of the name. So we've got 8 carbons, so that's going to be an octane. And then we have 3 double bonds, so that's going to be a triene. And then our double bonds start on 1, 3, and 5. So we're going to have octa, 1, 3, 5 triene. So that's going to be our parent name. So now we have to identify our substituents. So here we have a 1-carbon group, so that's going to be a methyl, and it starts on carbon 6. Coming off of carbon 4 here, we have a complex substituent. So we always start numbering from the carbon that's directly attached to the main chain. So we're going to start here with 1, and then we're going to go 2, 3. So this is going to be a propyl, and because we have that double bond, it's going to become a prop. 2 is where the double bond starts, and then ene-yle. And then this substituent also has its own substituent. So we're going to say that's our 1-methyl group, 1-carbon group coming off of carbon 1. And then since it's a complex substituent, we're just going to throw all of that into parentheses. And then remember, the number of where it's connected to the main chain goes out in front of the parentheses. So we're going to have 4-1, 4- parentheses 1-methyl prop 2 enil as that substituent. And aside from that, we don't have any other substituents. The last thing is going to be our stereochemistry. So we don't have any chiral carbons, but we do have double bonds. So we will have to look for E and Z. This double bond right here, we're not going to be doing E and Z because on the right side, the groups are both hydrogens, so you can't determine E and Z when the groups are the same on one side. For the double bonds starting at carbon 3, we do have different groups on each side, so we can do E and Z for this one. So we're going to identify our high and low priority groups. So on the right side, our hydrogen obviously is going to be lower than this carbon chain that we have up here. So I'm going to say our high priority goes on the up. On the other side, these ones are a bit more complex, so we're just going to start at the adjacent carbon and do our priority from there. So coming off of the main chain on this substituent, we have a carbon. It's attached to a carbon, and it has a hydrogen. The carbon 5 up at the top, this one is going to be carbon, and it's going to be carbon twice because it's double bonded. And then that one also has a hydrogen. So we can't determine the priority difference between these two, so we'll have to move on. So at the next carbon, we have carbon, carbon again, since it's double bonded, and then hydrogen. On carbon 6 up here, we've got carbon, carbon, and since this one is double bonded, we do go backwards, technically. So it's going to be carbon, carbon, carbon for this one. And so since this is our first point of difference and the group going up towards the top has the higher priority groups, we're going to go with the high priority on the top. So this one is going to be Z on the same side. So 3Z. This alkene out here to the far left, again, this one just has 2 hydrogens on the left side. So since those groups are the same, we can't determine priority between them. So this one does not have E and Z. And then starting at carbon 5, we do have different groups for all of these. So let me get a different color. So if we split this alkene down the middle, over on the left, we have a hydrogen versus a carbon group going down. So the bottom group is going to be our priority. And then on the right side, we have a carbon, it's a methyl group, so it's going to be H, H, H. And then at carbon 7, obviously we have a group bonded to a carbon. So this one is going to be CHH. And so that means the up side is going to get the priority. So in this one, we have down and we have up. So that's going to be opposite. And so that's going to be E. And since we have 2 substituent areas, we'll have to put the numbers to denote where they are. And that's all for stereochemistry. So now we just have to put all that together. So we've got 3Z, 6E, and then we put our substituents in alphabetical order. So they are both methyls, but since the group in red has a lot more stuff, that one's going to get that one's going to be put afterwards. So we're going to put the 6-methyl first, and then our longer group 4 in parentheses methyl 2 ene eel, and then close parentheses and the 1 3 5 tri. Okay. Any questions on that first one? Oh, sorry, you're right. That's my mistake. 5E. I was focusing too much on that one. 5. Any other questions? Mm-hmm. Yeah, that would be considered incorrect because for complex substituents, you put the whole substituent in the parentheses. Yeah. So for the double bonds, you can do either in the middle of the name or you can do them on the front, and either one's fine. Mm-hmm. Yes. So the prefixes are going to be if it's just a 1, it's going to be just regular alkene. Then it would be diene, triene, and then tetraene. Yeah. So tetra would be the next one after Try. I'm going to go ahead and move on for time's sake. So in this next one, we have a double bond, and we have a cyclic compound. So whenever you have a cyclic structure that has one double bond, again, our alkene is our priority group. So we want that one to have the lowest number possible. So it's always going to start with 1 whenever there's just 1 in the structure. So our parent name is going to be cyclohexene. And in this specific instance, if you put 1 cyclohexene or cyclohex-1-ene, that would be considered wrong. Personally, I don't really understand it, but IUPAC rules. So cyclohex-1-ene would be considered wrong. And it's just because if there's only 1 in the structure, then it's like kind of assumed that the double bond's at position 1, so it's just redundant to put the 1 in the name. So for this instance, we're just going to have cyclohexene without any numbers as our parent. And then for cyclic compounds, you have to be careful. So you could number around the ring in 2 ways. So the direction that we start numbering will affect the numbers of the substituents that we have. And so remember, we do want the alkene to get carbon 1 since it's our highest priority group. But we do also want to get the lowest numbers for the substituents as possible. So if we go around in red, we'll come to 2 substituents on 4 and then 2 substituents on 6. If we number around in blue, we'd get 2 substituents on 3 and then 2 substituents on 5. And so the first point of difference is going to be between the 3 and the 4s. So we're going to go with the numbering that gives us the 3s since those are the lower numbers. Okay. So then now we have to actually name the substituents. So we know that we have some ethyl groups here. They're 2 carbons. So these are all ethyl groups. So we have 3, 3, 5 triethyl. And then our last substituent is going to be this bromo. So this one's going to be 5 bromo. And those are all our substituents. So next we have to look at our stereochemistry. Sorry, my Siri is going off. Go away. Okay. So for stereochemistry, remember, priority is going to be basically what's lower on the periodic table. So bromine's going to be a higher priority than carbon. So here, bromine's going to be our first. We have a CHH. We have another CHH. And then we have a CHH. So we go to the next one. So on the bottom, we have a CCH. Up here on the top right, we have a C, C, and C because it has 2 ethyl substituents. And then the 1 ethyl substituent on carbon 5, that one's just going to be HHH because it's the last carbon in the chain. So the going to the top right is going to be our second priority, and then going to the bottom is going to be our third priority, and the ethyl group is going to be 4. So if we do our numbers, we get R, but since the lowest priority group is on a wedge, we're just going to flip that, so it's going to be S. So we're going to have 5S over here. And then even though we do have wedges and dashes for this carbon, this is actually not a chiral carbon because these groups are the same, so we can't assign it we can't assign it R or S. So we're just going to have the one stereo center. And so now I just have to put it all together. So since we just have one, you can do just the letter. So we have S, and then our alphabetical order for substituents. So 5-bromo, 3,3,5 triethyl, and then cyclohexene. Any questions about that one? Yes, so since it's just one, you don't have to put the number. If you would like to, if you put 5S, even if it's just one, that wouldn't be considered wrong. That's still okay. The only time that it's gonna make a difference is like with the thing we talked about at the beginning. But for the stereochemistry, you could put the number if you wanted to. Yeah, so we just look at the atoms that are attached to that chiral center, and we assign them priority based on it's whatever's lower on the periodic table is going to be higher priority. So bromine is obviously way lower than carbon. So that's why we put bromine as our first priority. And then our second priority, we had to look at the adjacent atoms, but the first atom that we looked at, they were all CHH. So they all had the same priority. So then from there, you just keep branching out until you find the first point of difference. And then for this example specifically, our first point of difference was here, here, and here. So the top right group got the higher priority because it was bonded to carbon, 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 and carbon. This group was bonded to carbon twice because it's a double bond, and then it has a hydrogen. And then the group on the substituent here, it's just a CH3 group, so just be HHH. So from there we could determine our priority. So then yeah, so the carbon, carbon, carbon one got second, the carbon, carbon, hydrogen got third, and then the hydrogen, hydrogen, hydrogen got the last one. And so then from there we can do our drawing. You just go from 1 to 2 to 3. But you have to watch out and make sure that the lowest priority group is not on a wedge. And if it is, you just flip the stereochemistry. So. It is faster, but usually faster comes with less accuracy, just in life. So I would say you could do that, but then maybe just double check. Yeah, you'll have time, so you should take your time and make sure you're going through and just checking everything. Because sometimes it does look like one might be the better group, but then it turns out there's like a point of difference that just makes it, I don't know, different. I've done it before in exams and I haven't gotten points off. For stereochemistry or for like the cyclohexene thing? Because I've had people. She did say that for stereochemistry specifically? Okay. I've done it before in exams and it's been okay, but I don't know, maybe she's changed it. Yeah, sorry. Yeah, so for anybody that didn't hear, James was saying, I couldn't think of the right word. So the priority is based on the atomic number. So going down, obviously, you have higher atomic numbers, but that's like the official definition. So you're never going to do E and Z when it's in the ring. If it's in a cyclic compound, you don't do E and Z. Only for linear chains. The atomic number, yeah. SJ. Yep. RNS is in linear and cyclic. E and Z is only going to be linear. Yeah, so groups that have carbons that have 4 different groups. Like for E and Z or R and S. So E and Z is going to apply to double bonds, and specifically double bonds that are in a linear chain, so not cyclic compounds like this one. And then R and S, usually it's when you see like the wedges and dashes, although not always, because as we saw in this one, the ethyl groups were both on they were on wedges and dashes, but we didn't do it in that case. So the official reason why you do R and S is when that carbon has 4 different groups. So that's why we didn't do it for this carbon here, because it has 2 ethyl groups. So if they're the same group, you can't do R and S. But for this one over here, all the groups are different, so then you do R and S. Yes. Mm-hmm. I'm gonna go ahead and move on, but I will get back to that at the end and we can hash it out a little bit further. Okay, so I'm gonna go on to the last question. So this one was supposed to be a Fisher projection question. You guys don't do Fisher, so I'm just gonna have us draw it for practice. I didn't really know what to do with it, so. So our parent chain is gonna be non-ane, so that's gonna be 9 carbons. So I'm just gonna draw a 9 carbon chain. So 9 carbons. We look at our substituents. So we have 2,6,8 trimethyl. So we've got a methyl group here. 2, 6, and 8. And then we have 4, 4, 5, 6 tetrabromo. So we've got bromine, 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 bromine. Just make it. Okay. And then we have 5R and 6S. So we have 5R, 5R and 6S. So I know that bromine is going to get our first, I'm just going to start at 5. Bromine gets our highest priority. If we go to the next carbon, and there's a hydrogen. If we go to the next carbon, we have a C bromine bromine. On the right, we have a C bromine. So the group on the left is going to get the higher priority because it has the more groups with higher atomic number. So this is going to be 2. And then compared to the hydrogen, the group on the right is obviously going to be a higher priority. We're going to have 1, 2, 3. So we do our arrow. That's going to be R. We want this to be R, so that's good. We're going to draw our bromine on the wedge and our hydrogen on the dash, so we don't flip it. And so that's going to be R. And then for 6, we've got a bromine, which is going to be our highest priority. We've got a methyl group, so this one's going to be H, H, H. This carbon is going to be C, H, H. And then this carbon is going to be C, B, R, H. So this group is going to be our next highest priority. So this is going to be 2. And then this group is going to be our third highest priority. So that's going to be 3. We're going to go 1, 2, 3. So that's going to be S. So again, just to lock in, so that's what we wanted, 6S. So to lock that in, we're just going to draw bromine on the dash, or sorry, on the wedge, and then the methyl group on the wedge. Sorry, go ahead. Yeah, sorry. The bromine on the wedge and the methyl group on the dash. So, yeah. I don't know what she's going to give you instead of this. It could just be like another nomenclature like the other ones we've looked at. I just wanted to do this one because I didn't want to like just skip over it entirely. So I thought it might be good practice to try it from the other. This is the first year she's done it, so I literally have no idea what she's going to do instead. So then this would be our final product. I didn't really hear you, but yeah. Yeah. Okay, so I'm gonna go ahead and move on. I'm gonna go to our facts questions. So I know that I think this one was asked on your first exam, correct? Do you guys want me to go over it, or you guys just want me to skip it? Awesome. That's what I like to hear. Okay. So moving on to the mechanism question. Answer the questions that follow. How many energy maxima would be present in the energy profile? So this is just fancy words for saying how many steps are there going to be. And that's just going to be however many arrows we see. So we have a fast step, a slow step, and a fast step. So we have 3 like arrow things. So we're going to have 3 energy peaks. So that's just like from the reaction diagram. So we'd have like a fast step, we'd have like a slow step, and then we have another fast step. So if this is like 1, this is 2, 3, 4. So we've got 1. This would be the product of that one, and then 3, and then 4. So yeah, it's just the number of steps that you see in the reaction. Any questions about that? Yep. So if it was just like A to B to C, you have 2 steps, so that would be 2. Okay, for the next question, the structure of the highest energy transition state. So the highest energy transition state is going to be the slow step. And if it asked you about lowest energy, I think this was on Hamza's exam yesterday, that would be any of the fast steps. And so that's just because the slow step requires the most energy to get over that peak. So the slow step will be the highest energy step as well. So we see here, we have the slow step. And so transition state drawings, you're just going to be drawing the bonds as they're shifting in that step. So I like to just start out with the reactant that we're given. We got this. And so in this step, the methanol is attaching itself to the carbon attached to the double bonded oxygen. So we're just going to draw a dotted line to the thing that's being, or the thing that's attacking. So that's going to be one of the lone pairs on the oxygen. And then we also noticed that the double bond has an arrow going towards the oxygen. So one of the double bonds, one of the bonds in that double bond is going to be kicked out and localized onto the oxygen. So we're also going to show a dotted line here with that double bond to show that that bond is also being broken. This one's being formed, so formed. And this one's broken. So yeah, so whenever you're drawing your transition state drawings, the dotted lines are going to show what's being broken or formed. And then the last step for this is going to be the partial charges. So we see that we have a partial charge on the oxygen in the reactant. So to show that changing, we're going to use the dipole notation. So it's going to be dipole positive. And so the dipole just means partial. So this means partial positive. And so we see in the end product, we don't have any charge anymore. So essentially what we're showing with that dipole positive is that charge is going from fully plus to partially plus, and then in the product, it's not charged. And then you'll also notice that in the product, we have a plus charge now on the oxygen that attacked. So it's kind of the same thing, but backwards. We're going to draw a partial positive on the oxygen on the bottom, because again, it's going from not charged to partially charged in this drawing that we have here, and then to fully charged in the product. So there's kind of three things that you have to do for this kind of question. You have to identify which step you're going to be drawing. You have to show the bonds that are being broken and formed, and you do that with like the dotted line. And then you have to identify any charges and make sure you draw like the partial charges on the transition state diagram or whatever. So it's going to be like the formal charge. So in this one here, we have oxygen, which has 6 valence electrons. It has 1, 2, 3 bonds, so -3. And then it also has a lone pair, so it's going to be -2. And that gives us +1. So that's where the charge comes from. And then as it reacts, and just using the same oxygen as an example, now we only have 2 bonds and we have 2 pairs of lone pair electrons. So we're going to have 6 valence electrons, and then we subtract our 2 bonds, and then we subtract all the electrons. So that's going to be -4. So now it's going to be neutrally charged. And so the transition state shows us the in-between. So we go from +1 to partially positive to 0. So it comes from the formal charge. Any questions on that one still? Yeah, I think it should be written because on this one it was written for you, so it should be. Okay. Yeah. If there's multiple, then you could choose whichever one. Usually if there's like a pick and choose, you'll see like draw the structure of an intermediate. So there's like multiple that we could do. So I feel like for the lowest energy step, it might be more likely that it's just 2 or 1 step. But yeah, you're right. I'm kind of just rambling. I'm not really making sense. Yeah, what you said, if there's multiple fast steps and it asks you to draw the lowest one, you just draw either of them. In the transition state, because the bonds are still shifting in the transition state. So we don't fully have the product yet. So we still have some of that bond left over, if you want to think about it that way. So it's still going to have slight partial charge. Once the bond is fully shifted and we're in our product, then it's going to be the neutral. Okay, I'm going to go ahead and move on to the next question. So draw the structure of an intermediate. So an intermediate is just going to be something that is formed but then is then used up in a subsequent step. So it's basically going to be anything that's not the reactant and not the product. So in this case, we have 2 options. We could draw the same one that we drew for the transition state one, or we could draw this one here, because those are both intermediates. So I'm just going to draw the other one just for fun, because we already drew the first one. And so in this case, it's not asking us about like a transition state or anything. It's just asking us to draw the structure. So we're literally just going to copy the structure that we have in the reaction. Make sure you put your charges and stuff too still. And so this would just be what we put in the box. Any questions on that one? Sorry? Yep. If it just asks you to draw an intermediate, yeah. Yeah, since you guys already asked it, it won't be on this exam. Okay, I'm gonna go ahead and move on. So that's all for that series of questions. So now we're looking at heat evolves per mole in a catalytic hydrogenation reaction. And so that just means we're adding hydrogens. And so for the heat evolved per mole, for more stable alkenes, we get less heat because they're more stable and they require less energy. For less stable alkenes, we're going to get more heat. So if it's asking for increasing heat evolved per mole, the highest is going to be the least stable and the lowest is going to be the most stable. And so remember, alkene stability, it's the number of carbon groups it has onto it. So if it has tetra sub, so 4 carbons, that's more than tri, that's more than di, and that's more than mono. So tetra is the most stable, and mono is the least stable. So then in terms of heat evolved, that would mean tetra is the least heat evolved, and mono is the most heat evolved. Does that make sense so far? Okay. So then we just have to look and see the alkenes that were given and how many substituents they have. So we have this alkene. It's got 1, 2, 3, 4. So tetra. In the middle, it has 1, 2. So this is di. And on the right, we have 1, 2, 3. So that one's tri. So again, the least sub is going to give us the most heat. So in the middle is going to be 3 since it's di. Tri is in the middle, so that one's going to be 2. And then 4 has the most subs, most stable, so the least heat, so 1. Any questions on that one? Sorry? So for alkene substituents, it's just going to be the number of carbons that you have attached. So if we look at something like this, we wouldn't count the hydrogens, we would count the carbons. So this one would be di-substituted. So it's just the carbons that are bonded to it. Okay, I'm gonna go ahead and move on. That was for the question that we skipped. Okay. So, again, for Fisher projection stuff, I honestly don't really have much of a clue what's gonna be on your exam in replacement. So I just went ahead and I drew the wedges and dashes for the structures that we were given. And so I'm just gonna go from there. So identical structural enantiomers or diastereomers. So identical is if it has the same stereo. Structural is going to be if it has different connectivity. And enantiomers, we've got mirror image. And diastereomers is going to be if at least one stereocenter stays the same and at least one switches. So diastereomers would look something like if we had an R, S, and then it went to an R and an R. If they both switch, so this is diastereomers. So kind of a prerequisite for diastereomers is that it has to have at least 2 chiral centers. So for this first question, we can't even have, or for A, we can't even have diastereomers. So we're just gonna not think about that for this one. I think the easiest thing to do for single carbon stereocenter molecules is just do the R and S priority, like numbering it and then finding the R or S. It's up to you though. So with this first one, we have bromine. That's going to be our number 1. Oxygen is 6 and nitrogen is 5. So oxygen is going to be 2, nitrogen is going to be 3, and then hydrogen is 4. So we've got 1, 2, 3. So this is going to be S. And our lowest group is on a dash, so we are good to go on that one. We don't have to switch it, I mean. On the other compound, we have bromine again. 1, 2, 3, and 4. So we have R, but our lowest priority group is on a wedge, so we have to flip it. So this one's going to be S. So this one, since they're both S, they're going to be identical because all the stereocenters are the same. Questions on that one? So, what I like to do for structural is I like to label the chiral center. So I just say like C1. And then between the two sides, I would look to see what's attached. So on the left-hand side, we have a bromine, an alcohol, or an OH. We have a NH2, and we have a hydrogen. On the right-hand side, we have a bromine, an OH, an NH2, and a hydrogen. So none of the groups are different. So this one is not going to be a structural. Structural is if one of the groups would be switched. Or for single chiral center, it'd be if one group is different. For multiple chiral centers, it'd be like if one of them was switched or something with the other one, or if there's just a totally different group on there. Yeah, no. The order is going to determine the stereochemistry if it's R or S, but yeah. Yes. Either a completely different group, or sometimes the tricky ones are like when the two chiral centers, like one of them switches, so it looks pretty similar, but it actually isn't. But, yeah. Mm-hmm. Yeah, they only changed positions. They did not change like the actual groups that are bonded to that carbon. So the changing positions is just going to be like the rotation. So you can rotate it, and like this one is just a rotation. They're both S, so it'd just be a rotation in some way. It would be different if one group is completely different on that carbon. So let's say like on the right-hand side, this wasn't an NH2, it was like a CH3 or something. Then we'd have structural because one of them has an NH2 and one of them has a CH3. Yeah. Okay, I'm going to go ahead and move on. So for the next question, we do have two chiral centers, so diastereomers is in the picture, so I'll have to watch out for that. So if we do a plane of symmetry down the middle, we don't immediately see enantiomers. That doesn't mean it's not enantiomers, but we kind of have to look a little bit further. So what I noticed with this one is we have a CHO on top, we have a CH3 on top on the right, we have a CH3 on bottom, and we have a CHO on bottom on the right. So I'm just going to check and see if we have a structural isomer. So I'm going to do what I did with the first one, where I label the carbons. So the top one is going to be carbon 1, bottom one is carbon 2. And I'm just going to see what's attached to those and check and see if we have structural isomers. So on the left-hand side, carbon 1, again, we have the CHO group, we have a hydrogen, we have a bromine, and then we have carbon 2. carbon 2, we have a Cl, we have a hydrogen, CH3, and then carbon 1. Now I'm going to check on the right-hand side. So on the right-hand side for carbon 1, we have a CH3, we have a bromine, hydrogen, and a, carbon 2. And then carbon 2 has a chlorine, a hydrogen, and carbon 1. So now we can look through carbon 1 from the left and the right and go through kind of like a checklist and see if they have the same thing. So carbon 1 on the left, we have a CHO. We don't have a CHO, actually, we don't have a CHO matching. We do have a hydrogen on both. We do have a bromine on both, and we do have carbon 2 on both. So this is a red flag. If we look at carbon 2 between the two structures, they both have a chlorine. They both have a hydrogen. This one doesn't match. And carbon 1 is the same. So you see here, we have a mismatch between the left and the right. So this one is going to be structural because the groups that are attached to each of those carbons are different. Not necessarily, because it could just be a rotation thing. Yeah. Yeah. So in this one, we like have an actual connectivity difference. So that's going to be our answer, structural. Yeah. So if we flipped it, I'm going to flip this one. H. So if you look here, H, chlorine, so now if we do like the checklist, carbon 1. Okay, so carbon 1, we have a CH3, we have a hydrogen, we have C2, but now the halides don't match. Carbon 2, we have a CHO, hydrogen, carbon 1, and again, the halides don't match. So this one, even if you flip it, it's still going to be. So for sake of time, I'm going to go ahead and move on. So this last one, again, this is kind of a Fisher projection question, but I don't really know what to do about it. So I'm just going to go with the easy option. I'm going to look for an antiomers. So I see that these two are mirror image. These two are mirror image. And these two are mirror image. These two up here are mirrored, and these two down here are mirrored. So this one looks like enantiomers. However, if you have an internal plane of symmetry in a molecule, so if you have chiral centers in a molecule, but that molecule has an internal plane of symmetry, it's going to be what's called a mesocompound. And mesocompounds are going to be identical to other mesocompounds. So we do have this plane of symmetry between the two, but if we look within each molecule, we can cut the middle bond in half. And I like to think of it like folding a sandwich or like folding a piece of bread or something. So we cut that in half, and we're allowed to do that. It's kind of weird, but we are. And we see that we have an internal plane of symmetry in each of these. And so that means these are going to be mesocompounds. And again, mesocompounds will be identical to other mesocompounds of that compound. So this one's actually going to be identical. Okay. Question. Yeah. James is saying on the exam, you can like rotate your paper around if it helps you to visualize it. Mm-hmm. Yeah. Yeah. They're identical because they're meso compounds, but it's asking you like which of the ones up here it is, so it's just identical. Okay, I'm gonna go ahead and move on. So the next question is asking for optical activity. And so this is just a fancy way of asking about chirality. So optically active compounds are chiral, and optically inactive compounds are achiral because they have either like a plane of symmetry or something like that where the rotation does not matter. So if we have a chiral compound, it will be optically active. If it's not chiral, it will be optically inactive. So for this first one, we have a double bond. And so remember for double bonds that it's planar. So when we're looking at this structure, the double bond is going to be in one plane, and then the cyclohexane is going to be forced in that same plane because it's attached to the double bond. And for this one, we see that we have CH3 and H, and we have like the wedges and dashes. So off of that cyclohexane, if you want to think about the substituents kind of like coming out of the page and going into the page towards you, the CH3 would be coming towards us and the hydrogen would be going into the page. And so if we cut that molecule down the middle, we would have a plane of symmetry, or we would not have a plane of symmetry because on one side we have a CH3, and on the other side away from us, we have an H. So this one is going to be chiral. I don't really know if that made much sense. And so that one's going to be optically active. Questions? Yes, that's a chiral center, but you have to double check and make sure there's not a plane of symmetry within the compound itself. Yeah, so this is a chiral center. I probably should have started with that. So this is a chiral center, but we still have to double check because sometimes even if it has a chiral center in the structure, there could be an internal plane of symmetry that causes it to be achiral. So it's kind of similar to the example that we did for C in the previous question. So even though all of these are chiral centers, because there's the internal plane of symmetry, then it actually makes it achiral. It depends on what those carbons are attached to. Yeah, so if we had like a CH3 versus a CH2CH3, so an ethyl versus a methyl, if you look at the first carbon that's attached to the chiral center, they're both carbons, but then they have different groups on them. So you kind of have to like keep going throughout the structure and look at all of them. Not technically, because the bottom group here is going to be adjacent to the hydrogen, and then the top group is going to be adjacent to the CO2H. Yeah, that's what she just asked. So if you keep going around the structure, you'll come to like this point, and then at this point would be the difference because on the top, this group is adjacent to the CO2H, and then this group is adjacent to the H. Yeah. Yeah, you gotta go like all the way until you find either a difference or it's like exactly the same. So if this part didn't exist, then you'd yeah. Okay, I'm gonna go ahead and move on to the next one. So anytime you see a chair on this test or a cyclohexane, be sure to draw your chair or draw your regular cyclohexane. So I just went ahead and drew my cyclohexane. We have these two CH3 groups. And so it may look like they're different at first. The bonding looks totally different in the chair conformation. We can see that these carbons are both on an up position. So they're both going to be either on a wedge or on a dash. They're going to be cis. And when we draw that, we have an internal plane of symmetry down the molecule like that. So this one is also going, or this one's going to be achiral because of the internal plane of symmetry between the two substituent carbons. So since it's achiral, it's going to be optically inactive. Questions? Like right here? The air. Like this? The only thing I can think I did was drawing the arrows, but oh, I think I drew like this. I was just showing like going like across the molecule. It's like I'm tracing the molecule. To see where I can find a point of difference. So it's like I'm looking at this one, and then I look at this one, and then I look at this one, and then I find my point of difference. I'll try to explain it afterwards, because it was just like something, it wasn't like anything super important that I was doing, but I'll explain to you after. What? This one here? Yeah. Okay, I'm gonna go over it afterwards. I don't want to get too caught up on this one, because we still have a lot to go through. So, yeah. Okay, so, like I said, I can go back to that question afterwards. I'm just gonna go ahead and move on. So question 6. So we have a question about the rate. So for these questions, you're going to have to identify if it's an SN1 or SN2 reaction. So you'll have to look at your halide and see what substitution it is. You'll have to look at your nucleophile. Yeah. So the halide that we're given here, it's the same substrate, and they're both a primary bromide. So primary we know is going to be SN2. And so for SN2, our rate equation is K times the substrate, concentration of the substrate, times the concentration of the nucleophile. So since we have the nucleophile in the rate equation, the nucleophile is going to play a role in the rate. And we can see that we're given 2 different nucleophiles, so we have to choose between them which one is the better nucleophile. And that one's going to give us the faster rate. So for nucleophilicity, there's kind of a few factors that you have to look at. I identified like this, I don't know, I tried to put together like a little flowchart for you guys. So definitely go back and review chapter 6, page 11. This is like the rules for nucleophilicity that she describes in the notes. So basically, what we're looking at in this question is just a difference between the atom. And so when we're just looking at the atom, the nucleophilicity is decreasing going to the left on the periodic table and down. Yeah, of course. Yeah, I can post it later. I'll post it later for you guys. But as I'm talking, you can also take a picture if you want. So the nucleophilicity for atoms is going to increase going to the right and down on the periodic table. So it's kind of opposite to electronegativity. So if we look at oxygen and nitrogen on the periodic table, nitrogen is to the left. So it's going to be a better nucleophile than oxygen. So in this question that we have here, Nitrogen is going to be the better nucleophile. And so that's going to give us the faster rate. So we're going to say B. Another type of question that you might be asked for this one is if it's an SN1 process. So let's say we had a tertiary bromide. So then we'd know it's going to be SN1. And so for SN1, the rate is going to be K times the concentration of the substrate. And just the substrate. The nucleophile does not play a role in the rate of SN1 processes because the first step is just the leaving group leaving. So if you're given a question asking about SN1, the difference in nucleophile is not going to make a difference. So if we were given this with either CH3OH or CH3 and H2, the rate would not be different between the two based on nucleophile alone. Yeah. It's more that like the ones that she gives us, the difference is just the yeah, I see what you mean. CH32. Yeah. The difference here is just gonna be the atom. Maybe if it was like a T-butoxide or something like that, like really bulky, but yeah. Questions on this one? So this example that I just drew off to the side, this one would be SN1 because it's tertiary. The one that we're given, they're both SN2. I just wanted to show you the example of the SN1 as well, because it's pretty important, and sometimes people forget that the rate is different between the two types of reactions. Mm-hmm. Yeah, so if it was SN1, and let's say the difference is going to be you're given a tertiary halide. Since the substrate is different, we know that SN1 favors tertiary over secondary, so then this one would be the faster rate. Yeah, for SN1, yeah. Okay, I'm going to go ahead and move on. So for question 7, if the compound would rapidly undergo E2, place yes in the box. If not, then place no. So again, if you see a cyclohexane, draw your chair. And if you see your chair, draw your cyclohexane. So for E2, we need trans-diaxial leaving group and hydrogen. And so basically what that means is we want the hydrogen and the leaving group to be on opposite sides. It's just the mechanism of the reaction. So we're given these cyclohexanes, and so we have to draw our chair conformation to see if the chlorine or the leaving group, it's chlorine in this case, if the leaving group is in a position to perform E2. So I'm just going to start with the T-butoxide group as carbon 1, because remember that our largest group has to go on the equatorial. So I'm just going to put that here. And then going around the ring, 1, 2, 3. I placed my T-butyl group on the up position. So since my chlorine is also on a wedge, it's also going to be in the up position. And then the next carbon over, we have a methyl and a hydrogen. The methyl is also on up, so it's also on a wedge, so it's also going to be in the up position. And so when we look at the chlorine in this case, we can see that it is in an equatorial position. And so if the leaving group is equatorial, it can't do E2 because it's not going to fulfill the trans-diaxial rule. So this one is going to be no. As for this one, again, we're going to start with our T-butyl group on the equatorial position, 2, 3. You see that the only difference between these two is the chlorine is either on the wedge or the dash. So I just know that the chlorine is going to be down in this case now. Again, the methyl group did not change, so that's still going to be on the up position. And then our hydrogens on the other groups. So we have our chlorine axial And when we look at the adjacent carbons, we do have a hydrogen that is also axial and trans to it. So this one fulfills the trans diaxial rule. And so this one's going to be yes. No, because the chlorine is equatorial. Axial. Yep. If it's equatorial, it's just kind of like, it's like in a pocket, you can't really access it. So it's not going to react in that case. Yeah. Yeah. I'll get you next. I'll do you next. Sorry. As the leaving group? It's because it's usually halides are good leaving groups. So that's always kind of like a hint. So bromine, chlorine, iodine. And in this case, it's just because it's like the biggest group when it leaves. So like a CH3 would not be a good leaving group. The halides usually have a lot of electron density to them, so they can kind of exist by themselves, so they're good at leaving. No. If you didn't have chlorine, this wouldn't do E2 at all. Yeah. You gotta have like a good leaving group. Other questions? Okay. I'm gonna go ahead and move on. Okay, we're at the reactions part. It's very fun. So this is basically just gonna be like an SN1, SN2, E1, E2 competition. So the last page of chapter 6 is like the page where she kind of fleshes that out for you. So go back and review that. Again, I put this together as kind of like a little flow chart, so you can like look at it and work through to find your answer. So again, I'll post this later too for you guys. So with this first question, we're given NaCN, we have CH3CN, we have XS. So if we look at our base strength, CN is going to be a weak base. So we're going to go this way. Weak base, nucleophiles. Remember that whenever you see Na, it's like an ionic interaction. So this one's going to be NaCN minus. And so our nucleophiles, negative charge is going to be a strong nucleophile. So then we're going to go this way. And so we know it's going to be SN2. So for SN2, remember stereochemistry. We have two potential leaving groups on this compound. We have the iodine and the chlorine. Again, halides are good leaving groups. Remember for SN2 though, we want it to be primary, secondary, tertiary. Methyl is also best. So the order of reactivity is going to be methyl first, then primary, then secondary, then tertiary. This chlorine here is attached to a secondary carbon. So it's not ideal, but it still will work. Now this iodine, however, it's attached to a carbon in a double bond. And so this is going to be an sp2 carbon. And the rule is that we do not do SN2 on sp2. That's like a little mnemonic that you can memorize. And for what it's worth, you wouldn't do any of the reactions on an sp2 carbon. So not SN1, SN2, E1, or E2. So since this iodine is on an sp2 carbon, it's not going to be reactive. So in our product, we're not going to do anything with it. Other than that, we don't have any other leaving groups. So it's going to be substitution. So we're just going to replace a nucleophile, which again is CN. And since it's SN2, we're going to invert the stereochemistry. So I just like to draw the groups where they were and switch where the other group was that didn't leave. So that would be our final product. Questions on that one? Okay. No. The only time you're going to draw, like, yeah. So the only time you'll have to draw mechanism sort of things is if there's resonance, or if it's like a series of reactions. I don't think we have one here, but on future exams, it'll be like 1 and then X and then 2. Yeah. So for this one, you'd have to draw like, oh, product of step 1 is A, product of step 2 is B. Yeah. So for this one, since we just have the one reaction, we don't have to do that. Okay. Next one. We have a halide. We have T-butoxide. And we're asked for the major product and only the major product. This is a secondary carbon, or it's attached to a secondary carbon. So if we go look at our flow chart, we have a negatively charged oxygen, and this is going to be a strong base. We're going to go this way. T-butoxide is going to be a bulky base. There's lots of substituents on this carbon here. So we're going to have a bulky base. So we're going to do E2. And I probably should have put this on the flow chart. So there's this thing called Zaitsev's rule. And no, it's not the Zaitsev in our department. And so this just tells you the where the alkene forms. So for small bases, it's going to form the more substituted alkene because it's the more stable product. However, bulky bases can't form the more substituted alkene because they're just too big. So even though it's technically less stable product, it's better for the base itself. So it's going to be less sub in this case because we have a bulky group. So as you can see, we could either form the double bond here or here. So this would give us the more substituted product, but again, we have the bulky base, so we're actually going to form the less sub alkene. So that's going to be our major product. So that's going to be our product of that reaction. Question. Yeah. The classic one is going to be T-butoxide. So you'll see this one a lot. It's possible that she could give you one that's like CH3, CH2, 3, N8, or sorry, N. So this is what that base would look like. And so again, there's lots of like substituents off of it, so it's going to be bulky. So just look at the formula that she gives you, and if it helps you to draw it out, then do that. And that's what I did here. And we can see that there's lots of substituents. Yep. Yeah, the CH3 minus, that's the T-butyl. So if you wrote it out with the condensed formula, this would be what that would look like. And then this is just like a shorthand version of writing it. Okay, I'm gonna go ahead and move on. So NBS and light. So this is going to be bromination. And this is specifically going to be allylic bromination. And so means carbon that's adjacent to a double bonded carbon. So we're just going to add a bromine at the allylic position. You'll see that we have 2 boxes. So what you need to know for NBS as well, kind of similar to the Br2 light, it's a radical reaction. So in the first step, we form a radical at the allylic position, and then the bromine gets added on. And so one of our products of this reaction is going to be simply adding the bromine at that position. Can you even do that? And then we can also do resonance with this radical. So that's going to form this alkene. We're going to have this alkene, or sorry, yeah, this alkene in the radical. And so then we could add the bromine at the new position. So then we just have it like that. Okay. Any questions on this one? In this case, since we're given 2 boxes, it's kind of a hint. The thing is, you'll just have to remember for NBS is that it does the radical formation. And if you have, well, I mean, you're going to have a double bond because it's the NBS. Yeah, NBS is like specifically for alkenes. So you'll just have to watch out and see if you can do any resonance. There might be a case where the adjacent carbon already has 4 bonds and you can't. So you'll just have to kind of be on the lookout. So the first position that you'll put it at is directly adjacent to the double bond. And so in this case, we're only given 1 position. We can't put it on this side because there's no other carbons, but we do have this position here. And so that is what we use to form our first product. And then we have another box, so we know that we have to form another product. And so this is just kind of like using your exam 1 knowledge. So we know that radicals can resonate with double bonds that are adjacent to them. So then we know, since we have that adjacent double bond, we can resonate it and form the resonance structure. And then from there, we can add at the new position. And then this would be basically. Yep. Yeah, just resonance. Yeah, everything is cumulative, so don't forget it. Okay, I'm gonna go ahead and move on. So this question, we're given a O-. That's going to be a strong base. It's going to be a small strong base since it's just an ethyl group. So if you follow the flow chart, you'll come to the conclusion that this is going to be an E2 process. So for E2, remember we need either transdiaxial for cyclic compounds, or it's called anti-coplanar in linear compounds. And so again, that just means that we want the hydrogen and the leaving group to be opposite to each other on adjacent carbons. So we see that we have hydrogen and we have fluorine, a halide, and they're opposite to each other. So this looks good at first, but spoiler alert, it doesn't work. Fluorine is actually considered a bad leaving group. And this is just because it's so small. It's the smallest atom on the periodic table, I think, aside from hydrogen. So since it's so small, it's actually not going to be a good leaving group. But we do have bromine. So we can use that as our leaving group. But since it's not anticoplanar yet, we're going to have to rotate the bond. So you can either, if it works for you visually, you can just kind of rotate it and redraw it. One thing you can do is you can do your Newman projection from exam 1. And so that's like the little stick line drawing with the circles. And so in the Newman projection, we would want our leaving group to be opposite to the hydrogen. So right now, what we have is we have this structure where the hydrogen and the fluorine are opposite. But since we know fluorine isn't going to be a good leaving group, we're going to have to rotate this so the bromine is basically where the fluorine is right now. So we're just going to rotate. I'm going to keep the front bond the same. H2. So I'm just going to put the bromine here, fluorine's going to go here, and CH2 is going to go there. That's going to look like. So now our hydrogen and bromine, our leaving group, are on the anticoplanar positions. So now we can actually do our E2. And so this is just going to form a double bond. And We know that the CH2 and the CH3 will be on the same side. And the CH3 and the fluorine will be on the same side. So this is going to be our product. And so the reason why it's important to do this rotation and check if you need to rotate it is because for starters, in this case, like this is just a bad leaving group, so you just get the wrong answer. But then also the stereochemistry of the final product will matter. So if you drew the stereochemistry flipped, if it was something like this, so this would be considered wrong that I just drew. And that's because remember that double bonds can't rotate. If it was a single bond, it wouldn't matter because it could just rotate, but double bonds can't, so that stereochemistry is locked in place. So if you have the wrong stereochemistry, then it's not like it can just rotate and fix itself. Yes. Yeah. So like from here. So once the double bond forms, it'll just become planar. So I like to think of it as I'm just like squishing them down, and then that's going to be like the plane. Doesn't really make that much sense. Yeah.
And then where we treat bromine, and then I start treating bromine as our leading.
Yes.
But then using that unit projection, should we also draw a chair conformation and check if the bromine is transdiaxial?
No, so transdiaxial is just going to be the version that you use for cyclohexanes. So this is not a cyclohexane. I just like to mention anticoplanar and transdiaxial together because it's the same concept. So in this case, we're going to go with anticoplanar because it's a linear compound. If it was a cyclohexane, then you would do the transdiaxial. So it's the same thing. It's just described differently because the structure is different. Yes, you will in the future. Not on this exam. Yes. Yeah. I'm gonna go ahead and move on. So our second page, again, this is great piece of art. Second page. So we have a CH3OH and we have heat. So anytime you see a ton of boxes like this and you see heat, this is a hint that it's going to be an SN1E1 process right off the bat. But again, you can walk through your little diagram. So we have a uncharged alcohol. So uncharged is going to be a weak nucleophile. Oh my god. So it's going to be a weak nucleophile. Weak base is the first one. It's a weak base because it's just OH, uncharged again. So it's a weak base. It's a weak nucleophile as well. So it's going to be SN1 and E1. And again, heat added just kind of allows more E1 product to form, but no matter what, E1 is always going to be a minor product. SN1 is always major over E1. They just put heat to show that you can form an E1 product. So for SN1 reaction, we have our leaving group, and then the first step is the leaving group is just going to leave. So we're going to be left with this carbocation. And so what we can do right off the bat is we can just take this methanol, and that can attach itself to that positive charge. And then we'll have OCH3. And then another equivalent of that base is going to deprotonate that hydrogen. And so we'll be left with this as our final product. So that's going to be one of our products. One important thing that you need to know is that if you have a carbocation and it can rearrange, it will. So we have a secondary carbocation here. And remember that we can do like hydride shifts, methyl shifts, all that fun stuff. So if we can form a more stable carbocation, the compound will do that. So what we can do here is we can do a hydride shift. And so this carbon is now going to be neutral, and the positive charge will be where we lost that hydrogen bond, or the hydrogen shifted from. And so again, this is going to be a tertiary carbocation, which is more stable than secondary. So this can happen, and it will. Yeah, if you draw it on either side, it'd be okay. And so from here, we can do another version of the SN1 where the methanol attacks. And for sake of time, I'm not going to draw the full mechanism out, but our product would look like this. Okay. So now I have two more boxes, and you'll notice that they say minor. And so again, E1 is always going to be minor to SN1. So now we just have to look and identify what the E1 products are going to be. So I'm just going to start kind of back from here. We have hydrogens adjacent that we could take off. So get my base here. This is going to deprotonate that hydrogen, and that's going to shift in to form the double bond. So that's going to be one of our products. And again, if it can rearrange, it will. So we're just going to start from here after the hydride shift. So we could pull hydrogen from the right, or we could pull it from one of these CH3 groups. If we take off the hydrogen on the right, we're just going to form the same product that we already formed up here. So we're instead going to pull from one of the ones on the left, or on top. So this is just going to take a hydrogen. That's going to give its bond towards the positive charge. So then our final product would be this. Questions on that one? U1 is never ever going to be major, like ever. And the reason for that is, so for the first step of both SN1 and E1, the leaving group leaves and forms a carbocation. And so for SN1, the nucleophile can then just attach itself. So the negative density, like electron density, can attach itself to the positive charge. For E1, what happens is the electron density ignores that positive charge and just goes for a hydrogen. So it's just not very energetically favorable. The negative charge won't directly be attached to the positive charge. It'll just go towards the hydrogen instead. So that's going to take more energy for that reaction to happen. So even if you add heat, it's still going to be a minor product. In the notes where she does like the SN1 E1 competition, she writes like the percentages of like how much is formed. And so for the example she gives for the SN1 versus the E1, it goes from like 97% SN1 and like 3% E1. With heat, it goes to like 80% SN1 and 20% E1. So it's still a minor product. It's just that you can form a little bit more of it. It's not with SN2 and E2. So E2 is E2 is more energetically favorable because you don't form like a carbocation and then have to take off the hydrogen. It happens at the same time. Yeah. So this is kind of just like the SN1, E1 together. Yep. That's just because like you could draw the wedges and dashes, but since you just have to have a lot more boxes, basically. You'd have to be able to draw that one, and then you'd have to be able to draw this one, and then you'd have to draw this one. So, yeah. I think she just doesn't really care to ask you about the stereochemistry of it because it's going to be 50-50 either way. So this is kind of like a 50-50 mixture of the stereochemistry product. I don't think so. As long as you have like these two different structures. So if your two answers were like this and then this, then this one would be wrong, or one of them would be wrong because it's the same structure, just different stereochemistry. And for SN1 it'd be 50-50. So this is just kind of redundant. So as long as you have like these two, like you could put that one on a wedge and maybe put it on a wedge here. That should still be okay. But yeah, you just gotta have the different structures. I'm gonna go ahead and move on. So we have our last reaction question. Again, we have major and minor, so be on the lookout for that. So we have an O minus, so this is going to be a strong base. And it's a CH3O minus, so it's going to be a small strong base. So if we go to our flow chart, we have a strong base, we have a small strong base, and then you'll notice this like additional step here, primary, secondary, or tertiary. So if we look at the carbon that this OTOS is attached to, this is a primary carbon because it just has this one carbon group. So we go back to our flow chart, and primary is actually going to be SN2. So even though this is a strong base, it's a small strong base, and the halide is primary. So the major product for this is going to be SN2. And so that's just going to be the substitution. And we're not given stereochemistry. This is not a chiral center anyways because it's two hydrogens. So you'll just have to draw the nucleophile attaching. So that's going to be our SN2 product. If you're given one box, I would probably just leave it at that. That's going to be your major product. Since we're given the minor product, we know that this strong base will also do some E2. And so from there, we just do the E2 reaction. So we have our leaving group. We have an adjacent. We have an adjacent hydrogen. So this is going to leave the base. It's going to take off the hydrogen. That's going to come back and form our double bond. Not in this case. So this is just going to be, oops. This is just going to be E2. Since we don't form a carbocation, we don't have to do any hydride or methyl shifts. This happens in one step. So the leaving group leaves and the base attacks at the same time. Yeah. You probably could see this one as just like one box for your answer, and then you just have to draw the SN2 product. But since it shows major and minor, you're just going to draw the E2 as a minor product. I'm not sure. Yeah. I'll have to think about it. Yeah. So the reason why this one is SN2 major is because we go through our flowchart and we have a strong base because it's O minus. It's a small strong base because it's CH3 O minus. And then the last step for that side of the flowchart is the type of carbon it's attached to. So primary or secondary and tertiary. Oh, sorry, I didn't hear you very well. Okay. Yeah, so in this case, we can only draw it in one position because it's on the end of the chain. So this leaves, and then we're going to draw the double bonds between those two carbons. Yep. Yep. I'm going to go ahead and move on to mechanism. Yay. Okay. So this again is just going to be like some form of SN1, SN2, etc. So we are given H2O and heat. So H2O is a weak base, and it's a weak nucleophile. So this is going to be SN1, and then with heat, it's going to be SN1 and a little bit of E1. So our first step for either of these two reactions is the leaving group is going to leave. So we're going to be left with this. And so whenever you're doing your mechanism questions, always be sure you're checking with your product just to make sure you're kind of following the right path. So I can see that I have a OH added on. We do a ring expansion for this one. However, for this first product, we don't directly add the OH onto this carbon here. Instead, you'll see it's added onto this carbon. And so what that tells me is we're going to do a methyl shift, or sorry, not methyl shift, hydride shift. So again, this is a secondary carbocation. If we do a hydride shift, that puts the positive charge now on a tertiary carbon. So we go from secondary to tertiary. So this is a good hydride shift. And now from here, we can attach our OH to our molecule. So we're going to attach our nucleophile. It's going to attach the positive charge. And we still have both of those hydrogens attached onto that water molecule that we just used. So before we can have our final answer, we got to do one last deprotonation step. Oops. So we're just going to take another equivalent of our base, and that's going to take off one of the hydrogens on that water, and it's going to leave us with our final product. So that's A. Any questions on that part? Mm-hmm. Yeah, so the reason why I used the one off of the Cyclic group, it's partially just because I'm looking at the product and I see that the nucleophile attached to this position. So if I were to do a hydride shift with the other side, so like from this hydrogen here, so that would give us a carbocation on a vinyl position, so on a double bonded carbon. And so this is a very unstable carbocation, even more so than the secondary one that we came from. So it's partially that, and then also partially just because when I check with the products that we can form, we're putting the nucleophile in a different position. Mm-hmm. You mean like if it's on the bottom or on the top? Yeah, this would be fine. Yeah. Either one is fine. But if you want to, you can make sure it looks exactly like. Yeah. Okay. So the next part, we have to do a ring expansion. We go from a 5-carbon chain to a 6-carbon chain. So these ones can be tricky. So what I like to do is I'd like to start numbering from somewhere on the compound that stays relatively the same. So you'll see in all of these structures, we have like this double bonds like branch coming off. So I'm going to start that. 7, 8. And this is just a way to keep track in your mind and make sure you're not losing any bonds or drawing the bonds to the wrong positions. So it's not like IUPAC where you have to like number it properly. So you can number it however which way works best for you. I'm going to redraw starting. So I'm just going to do a redraw so I can, I don't know, separate these two. So I'm going to number this one as well. 3, 4. Okay. So I see in the structure we went from 5 carbons to 6 carbons, and it looks like we also formed an additional double bond. The first thing I'm going to do is do the ring expansion. So I can see that we went from, where is it? We went from 3 and 4 here. Now 3 and 4 are here. So we formed a bond between 3 and 8. So I'm going to draw an arrow from the bond between 4 and 8 towards the positive charge on carbon 3. And okay, so we went from a bond between 4 and 8 to a bond between 3 and 8. So we broke this bond. 8 still has a bond attached to one of those. So here it's attached to carbon 4. Here it's attached to carbon 3. Carbon 3 went from positive to now it's neutral because it gained a bond. So 4 is going to be where our new carbocation is going to be because it lost the bond between 8. So that's kind of what we lost right there. Sorry? What do you mean? The 8 kind of attacks 3. Yeah. Yeah. So now we have this carbocation. If you look in the final product, we have, right now we have a double bond between 5 and 6. In the final product, we have a double bond between 5 and 6. I think I numbered it wrong. So now we have a double bond between 4 and 5 and 6 and 7 in the product. So we're going to have to resonate the double bond that we have currently to form the double bond between 4 and 5. So we're going to have 4 and 5, 2. So that's going to leave a positive on carbon 6. So now we have a double bond between 4 and 5. So we're kind of one step closer. Now we need to form the double bond between 6 and 7. And so the way we can do this is through an elimination reaction. So this would be like an E1. So we're just going to take our nucleophile, our H2O. We're going to take an adjacent hydrogen. Nucleophile is going to take the hydrogen, and that bond is going to shift in towards the positive charge. So then we're going to be left with 2 double bonds in our structure. And so it's kind of rotated a little bit differently, but this is product B. Any questions on mechanism? Okay. Mm-hmm.
And if you look at the primary shift, the second product, just above your final product, which you labeled A.
Mm-hmm.
Could you explain that little area that you H to the oxygen? Could you explain that hydride shift?
Mm-hmm. I'm gonna wait a second for people to take a picture. Mm-hmm. Sorry. My fat head.
Could you explain that hydride?
Mm-hmm. So you're talking about right here?
Oh,
Yeah, this one?
yes.
Yeah. So that's not a hydride shift. So what's happening is the H2O, the nucleophile or the base, it's taking that hydrogen away from that oxygen. And then the arrow is showing that the electrons from that hydrogen is going back towards the oxygen. And that forms the lone pair that we gain.
Also,
Yep. So the hydrogen goes to the H2O that took it. So it'd be H3O plus now. But we don't have to draw that because it's not one of the products in the top part. Mm-hmm. Down here. Mm-hmm. So you may or may not have to do this on a mechanism on your exam. This one, again, I'm just kind of using the product to guide myself. So in the product, if I didn't have to do resonance, then I would just have this. But so that would be like what this is. Again, it's kind of rotated slightly differently. But I see that instead we have double bonds at different positions. So I'm just going to resonate the double bond that we have currently towards the positive charge to get that double bond in a different position, and then do my elimination reaction to form the second double bond. Mm-hmm. Other questions on mechanism? I'll give people a second to take a picture, and then I'm going to move on. Sorry? Yeah. Okay, I'm going to go ahead and move on to synthesis. Damn, 7:50. Okay, so again, like everything else on this test, this is going to be largely your SN1, SN2, E1, E2 stuff. You'll also have some bromine and light and NBS and light reactions. So make sure you check with the instructions and see what you are allowed to start with. So we can start with alkanes, 4 carbons or less, or cyclohexane. That's not what I wanted. So then I'm just going to find somewhere on the molecule to cut and work backwards from. So if I cut the bond between the oxygen and the cyclohexane, then I will be left with this and this. And we're going to put heat over the arrow. So this is going to be an SN1 reaction. We have a secondary halide. We have the OH. And those are going to join together to form the end product as an SN1 reaction. You kind of got to think forwards and backwards at the same time. So always make sure you're like double checking your work at each step. So then from here, we have to keep working these back until we get to either cyclohexane or the 4-carbon alkane. So I'm just going to start with the one on the left. So this is going to be just another substitution reaction. So for substitution reactions, we need our halide. And then if we want to put an OH onto the molecule, we're going to use a nucleophile that would allow us to do that. So we're going to use H2O, or you could do OH minus. Either of those would be okay. In this case, I'd probably go with OH minus because we have a primary halide, so it'd be more of an SN2 reaction. And then from here, we have an allylic bromide. So we need to do a bromination reaction. And so whenever you have an alkene, the bromination reaction you're going to use is going to be the NBS and light reaction. And so that's just going to give us the allylic bromide. So now we have a double bond, and we know to form double bonds, we need to do an elimination reaction. So I'm going to use a halide, and then I'm just going to do an E2 base. So I'm just going to do like CH3O minus. And so this would give us an E2 reaction. Going forwards, so E2. And then to work this back to an alkane, we're just going to do another bromination reaction, going backwards. And so we're just going to do Br2 and light. And then whenever we do a Br2 light reaction, we always want to do excess for the starting material because bromination reactions tend to add multiple halogens. So you just want to put excess to show that you only want the one addition. And so if we count this, this is a propyl, it's 3 carbons, so that's 4 carbons or less, so we're good to go with this one. Any questions on this side? Okay. And it's basically just going to be kind of something similar on the other side, just halogenations and then substitutions or eliminations. So we have a bromine. It is adjacent to a double bond. So we're going to use our NBS and light. So our starting material is just going to be the double bonds. So to form a double bond, we need to do an elimination reaction. So our starting material is going to be a halide. And then for our base, again, I'm just going to do like CH3O minus, strong base to do E2. It doesn't have to be. Just watch out and make sure the one that you're using will form the product that you desire, which is kind of an obvious statement. But just remember that like if it's small, it'll do the less substituted. If it's bulky, it'll do the if it's small, it'll do the more substituted. If it's bulky, it'll do the less substituted. And then again, we have another allylic bromide, so we're just going to do another NBS and light. So now we have that as our double bonds. We're going to do another elimination reaction. We have a bromine. And then here we can just do a Br2 light and have our cyclohexane. And then remember excess. Questions on synthesis? Yeah, like if you put it down here. Yeah, that's fine. Okay. Thanks for coming, everybody. We'll be here for questions for a few more minutes. Otherwise, go forth and do your best. Okay. I'm gonna stop my broadcast real quick and I'll go back to it.